All right, hi everybody. We are going to start today's CTL presentation. Very excited to hear about a new NFT methodology using some mathematical modeling. And with that, I'm just going to go ahead and let you take it away. Please tell us all about it.
All right, thank you very much, everybody. If you are watching this later, or you are here now. So yes, I'm going to be using some mathematics, and I built some NFTs. These are non-fungible tokens. Non-fungible tokens, they have so uniqueness because of their identity as a digital file that is on blockchain, that sort of thing. But I'm going to introduce some additional aspect to this. Namely, kind of uniqueness, or let us say rarity, with respect to some mathematical properties that I'm going to be talking about. So let me share the screen and tell you what I start from, like some simple puzzles, if you would, and then go a few levels up from there. I guess I am already sharing the screen. All right, so yes, let's look at these so to speak, threes. So I'm referring to these as ternary trees because I start from a root. This is the root of the tree. Sometimes the trees grow up, sometimes they go down. And when they go down, we talk about their depth instead of their height. So just for writing purposes, these trees go down and I have a root here. And then as I said, these trees are ternary. So meaning from each node, I would have 3 branches out. And then this is a like 2 generation or 2 levels. This is of depth 2, each of these trees. By the way, what you see at the left, these are labels of the trees. I generated a bunch of these of depth 2, and I have labeled the edges. So I have a tree which starts from the root like there. It has 3 branches here, and then each of those nodes or children of the root of the parent, each of those would have 3 children of their own. So we have 3 branches from those. If we stop at that level, we have a complete ternary tree of depth 2, and we have labeled the edges with either 0 or 1. And the question is, if I want to extract a binary subtree of this ternary tree. So in other words, at each level, I'm going to keep 2 and remove 1 branch. So at the first level, you are allowed to remove one branch and keep 2. And when you go to the next one, from the ones that you have kept, you are going to remove 1 branch and keep 2, and do this until you reach the end of the tree. For these trees of depth 2, after a couple of steps, you reach the end, the terminal nodes or leaves of the tree. So what I wrote here on the right, this is, so to speak, their weight. What do I mean when I say that the weight of this tree is 2, and for example, this one is 1? It means that if I extract a binary subtree of this ternary tree, meaning removing 1 branch at each level, keeping 2, do this process, reach the terminal nodes, and then see how many path labels you have used. So let's look at this simpler one, the third tree. This is tree number 3, which I'm claiming has weight 1 in the following sense. So there is a binary subtree of this third one, which uses only 1 path label. You see, all the first branches are labeled 1, so that makes the weight smaller. And then when I look at the next generation, this one has the majority of 1, this one has the majority of 0, and this last branch has majority 0 also. So of course, if I want to minimize, if this is a game, somebody gave me this, somebody designed this tree, gave it to me and asked me find the simplest binary subtree in the sense that it uses the minimum number of path labels. Of course, the other gamer, the other person is going to say, well, how about 1, 0, 0 here, and then 1, 0, 0. So in other words, with the path label 1, 0, in other words, a sequence of length 2 of zeros and ones, in this case, just 1 0, you are able to extract a binary subtree of this. Put it in another way, if you extract only the paths starting from the root, going all the way to the terminal roots, terminal nodes, keeping only the nodes that use path label 1 0, there is enough of them so that a binary subtree is included in there. Look at this. There is also another one here, 1 0. There is another branch here, 1 0. But I'm not going to use that because it's not going to be part of the binary. If I want to make it binary there, I would have to use 1 1 also, which would increase the number of path labels used. So if I want to use just 1 0, this middle one is good, and the last one. So I have the same edge labels at the beginning, first level, and then the majority for these two coincide, namely 0. That makes it possible to say that the path label 1 0 is enough to extract a binary subtree from this. You see, 1 0 here, these 4 nodes, these two together with these two, they are enough to give me a binary subtree. So the weight of this tree is therefore 1, meaning that the minimum number of path labels that I would need to extract a binary subtree for this particular labeling of the 3 is 1. But for the other two above it, 1 would not be enough. Look at this one, for example. If you want to use the 0 and 0, so the majority at the first level is 0. If you want to take advantage of that, when you go to the next level, the one that started with 0, the majority here is 1, whereas the majority on the other end is 0. So if you use these two branches, you would have to use 0 1 and 0 0. That would make it 2 path labels, 0 1 and 0 0. If you want to use that middle one together with one of these, it's already separating. One of them starts with 1, the other one starts with 0. And so they would be, there would be two of them. So you cannot extract a binary subtree of this with fewer than 2. Whereas for the third 3 here, just randomly generated, you could do that. Okay, so that's the idea, weight of a 3. So when the depth is 2, we only have the possibilities of 1 and 2 for the weight. And here is some trees of depth 3 now. And to the left, you see just their labels. And to the right, you will see their weights in the same sense. Namely, if I want to extract from this 3 number 1 on the left, if I want to extract a binary subtree starting from the root at each level, at each generation, just keep 2 of them, 2 of the branches, and remove 1. Go to the next level, do the same, just following the ones that you have kept. If you remove, for example, this branch at the beginning, then you are not going to continue for the children of that branch. So you extract the binary subtree. No matter what you do it for this particular 3, you are not going to be able to extract a binary subtree using fewer than 2 path labels. Whereas for this 3 below it, it is possible to do it with 1. And there should be some which require 3. If it's not, then we could generate. So in this particular generation here, I don't have a 3, but I could run my program hopefully. And because 3 is fewer, okay, so 3 is more frequent, okay, and I'm labeling these randomly. So I'm running the program again. Did I get a 3 this time? So you see, 3 is not as frequent. So let me see if I can do this a few times and I get a 3. If not, then I would have to maybe create more than. So you see here, I'm creating 10 of them. And in the few 10s that I generated, I did not get a 3. Right here. Okay, so after a few times, I did get a 3 now. So it means that this one it is shown that I show in my paper that for trees of depth 3, number 3, as the maximum of minimum of number of path labels is possible. What do we mean here? Maximum of minimum. So in other words, you are going to change the labelings, put different choices of zeros and ones on the edges, and try to extract binary subtrees, starting from the root, reaching the nodes, the terminal nodes, the leaves, and see how many path labels are possible as a minimum for that particular labeling. But then you change the labeling, as I just did. I ran the program a few times, changed the labeling, and I came up with an example of a ternary tree of depth 3, which has weight 3. Namely, for this tree, to extract a binary subtree, you cannot do it with fewer than 3 path labels. I will have another file, which we'll go over this, hopefully, if we have time, in some other words, and I show you some statistics there as well. So then we go one depth higher. So how about depth 4? In depth 2 and 3, I have the exact expected value of what the weight is. When we get to weight 4, it becomes much more difficult because the number of trees is so large that we cannot do that exact thing. So we approach it with some theory as much as we could and with some simulation. Then the simulation gives me, for example, here I ran this thing for over 100 trees, and it is shown, we show that the weight of trees of depth 4 is either 1 or 2 or 3 or 4. So in other words, no matter how you edge label the branches. By the way, the reason that this is drawn this way, kind of circular in depth 4, is because we want to use more space, because this is the way mathematical software or computer algebra system, Wolfram Mathematica does it. We want to use, because otherwise it would be so dense down here that it would be even more difficult to read than this. So we use the space above it, make it more circular, and that's a tree of depth 4, as you see. Start from the root, then first generation, then second, then third, and finally fourth generation. You label each of these edges by either 0 and 1, and you are looking for the same thing, namely a binary subtree that uses the minimum number of path labels. And for this particular one, my program says that the weight is 2. So in other words, for this, there is a binary subtree that uses 2 path labels. And for this particular labeling, there wouldn't be any that uses fewer than 2. So in other words, you cannot do you cannot extract a binary subtree of this particular tree, which uses only 1 path labels, and it still includes a binary subtree. So then here is another one, a particular one. Something strange happens. You would think that if I start my first generation with the same labeling, we might think that it would make it simple. It might not get to the full weight of 4, but actually that impression is wrong. So it is possible to start the first generation with the same label, for example, 0, and still come up with the maximum possible weight. This property is used when I construct trees of depth 5, because now if I have 2 of these, one exactly as you see here, and the other one, so to speak, the dual to this, when I change the labeling at the first level, all 3 zeros, I change it to 1, and I consider these 2 as to be dual. And then for my tree of depth 5, I would start with the same label, for example, 0 and 0, and put these 2 things, the dual things, next to that. And because they differ at that top level, so not the very top level, but 0, 0, and after that, one of them has all 3 zeros, the other one has all 3 ones. So that distinction makes the tree of depth 5 that you generate to require the maximum number, which turns out to be, as an interesting theorem, to be 8. So in other words, the function that we are dealing with here starts with f of 1 is 1, f of 2 is 2, f of 3 is 3, f of 4 is 4. You think it's identity? No. Then f of 5 is all of a sudden it's 8. So when we go to that, we will see. So this is another verification of that, that the weight was 4 there. And then trees of weight 5. I would certainly have much bigger versions of this when you would be able to read the labels, but this is a verification or a way to calculate the weight. And when I show you other NFTs, so these weights, the 443, so the 443 would refer to the weight of the 3 children. So let us say the Northwest, the South, and the Northeast children of these 3 of depth 5. They would have this particular one. Those would have weights 443. And if you compare pairs of them in the order that I mentioned, it would be 8. So one pair of them requires 8. One pair of them requires 4. One pair of them requires 6. But because the first generation, because of the way that the first generation is labeled that particular way, it makes the weight of the whole 3 equal to 7. 7 is going to be one of those rare things. If you generate these things randomly, if you label the edges randomly of 3 of depth 5, often you get 4. More than 55% is going to be 4. About 18% would be 5. About 23% would be 3. And 2 and 6, about 1% or 1.5%. Most likely you are not going to get weight 1, you are not going to get weight 7, and you are not going to get weight 8. Those things require special construction. Otherwise, you are on your own, try billions of times, and most likely you will not get those. So this is a this is a random generation. I can run it again if I had time, but this is a random generation. I just randomly generated 2 of these, and one of them turned out to have weight 3 and the other one weight 4, right? These are among the 3 that are most frequent, 3, 4, 5. So now let me also tell you that I considered 4 particular functions that are related to something that's called Z numbers. A Z number would be a real number, so that when you multiply by powers of 2/3 and keep going, multiply by 2/3, see what the integer part, what the fractional part is. Is it less than a half? Because the fractional part of a number is going to be between 0 and 1. Left close, right open. It could be 0, potentially. It could not be 1. So the question, Mahler's question was whether or not there are Z numbers. So in other words, when you multiply repeatedly by powers of 2/3, is it possible that all the time, forever, you get fractional parts that are less than a half? So a version of that problem that I worked with was starting from your number and multiply by 2/3 and take the floor of that. And when you get to a number that's 1 modulo 3, it means that when you get to a number which has remainder 1 when divided by 3, it's better to stop, because then the process would not be recoverable. It's not undoable. If you want to undo the process, go back, take the inverse function. When you reach the something that has remainder 1 by 3, that would not be doable. So these things are present in my first and second generation of the NFTs that I generated. So I can now show you, hopefully, so let me stop the share and then share the other one, I guess, the other file that I wanted to share. So let's look at this. So some of the stuff I'm going to repeat so people would have a better idea of what's going on. So we started with trees of depth 2. These are some other examples. Labels to the left, weights to the right. And then I calculated the probability that the weight is 1. So 5/8 of the time, for depth 2, 5/8 of the time, the weight is going to be 1. And the remaining 3/8 of the time, the weight is going to be 2. And here's a short proof of that. And then how about depth 3? So one further level, depth 3. Still, we are able to calculate the exact probability distribution of the possible weights of 1, 2, 3. And therefore, we would be able to easily say what the expected value of the weight is. So the probability that in depth 3, the probability that the weight is 1 is going to be 2,275 over 16,384, which is roughly 13 or 14%. And in depth 2, if we have the exact value, is roughly 83%. And for weight 3 is roughly 3%. And then when we calculate the mean, it's going to be roughly 1.9 or so. That's for depth 3. And these are some other examples similar to the other file I showed you. And this is some distribution sampling of in depth 4. Right. So, for example, the last row is when I did it 1,000,000 times for depth 4 now. And you see, wait, so how many? So the frequency of number of times or threes, randomly generated threes, ternary threes of depth 4, edge label randomly with zeros and ones, and only 3,597 were of weight 1, and then over 360,000 weight 2, over 564,000 weight 3, and about 71,000 or so weight 4. And this is another run of the program. Of course, when you simulate, you are going to get slightly or different numbers. But they are, as you increase the sample size, they are getting closer. So that, together with some mathematical arguments that I gave here for at least one of the cases for weight 1, tells us that roughly 0.4% in depth 4, roughly 0.4%, smaller than that, less than that, would be of weight 1. About 36% would be of weight 2. About 56% or more would be of weight 3, and about 7% would be of weight 4. And notice that we are talking about a universe which has more than 10 to the power 36 depth for threes. I think, if I'm not mistaken, they say that the age of the universe is probably 10 to the 27 seconds. I'm sure you see this is more than that. And then we go to depth 5, which is even much, much bigger than this. So these are some confidence intervals for the mean. One of the goals of this project was to calculate or estimate the mean, because the universe is so huge here, you cannot do all of them. So this population, so to speak, is so huge. Of course, you want to do the sample and calculate the mean for that sample, mean weight for that sample, and then say do the confidence interval. These are the confidence interval. I guess I did at the level of 99%. And these are some other trees of depth 4. So here you probably see them better if just look at one of these. So the very first one, top left, is weight 1, then weight 2 here that I'm looking at. This is weight 2. And then the extracted binary subtree is highlighted. So the good thing is to just, once again, to remember what we are talking about. The whole idea was we have a ternary 3, and at each level, we are removing one branch, keeping 2. The 2 that I kept are highlighted. I go, so continuing these kept branches, I go to the next level, remove 1. So that one is not highlighted, but the other 2 are highlighted. And similarly here, keep going until you reach the final nodes, the terminal nodes or leaves, and see how many path labels you have used. So for example, 1, so no, sorry, start from here. 0, 1, 1, 1 is one of them, right? 0, 1, 1, 1. So for depth 3, the sequences, the path labels will be of length 4. This is one of them, 0, 1, 1, 1. What is the other one? So here is, okay, so what else besides 0, 1, 1, 1 we have used? It's this one here. You see 0, 1, 0. Okay, so you see here they are different here. So and then the rest of them are similar to so they are the same as one of these 2 branches. So that one uses 2. So I have examples of 1 through 4, and then depth 5. I constructed weight 1 through 8, many of them. But the more rare they are, I wanted to construct more of those. So the more rare they are, more interesting. So what is so things that are rare, special, I mean, if they are difficult to construct, they would be of interest, okay? So weight 1 has a special situation because it's rare. You are most likely not going to end up with one if you just randomly label the edges. But it is easy to construct nevertheless, because you could start from a ternary tree of depth 5 without edge labels, and then consider a binary subtree as you wish, and then put just one label on those, one path label on those, and then color, so to speak, the rest of the edges arbitrarily, and then there is a hidden binary subtree which uses only one path label. So it would make the weight of the whole tree equal to 1. So rare but easy to construct. So is this very interesting? No. So that's why I constructed about 250 of those as my NFTs. And I, in terms of the, so by the way, when I wrote this preprint, I started with having like over 1,000 or 1,500 supplements. I needed a place for these supplements to be posted. And of course, journal papers cannot have that many supplements. So I found this place to post them. So double benefits. I post them as supplements to my paper, and they are also there for people if they want to, so to speak, own them. And weight 1 is the least exciting, and so I listed those things like at 1 over 10,000. So 1% of 1% of an Ethereum, which when I did that, it was about 18 cents. Maybe it's about the same thing. So things like that. There will be a link at the end. And then weight 2. Oh, sorry, what I said about the rarity was, what I just said was about 4. Okay, 1 was a slightly higher because 4 is the weight 4 is the most. I told you it's about 55%. If 55% of the time you end up with something that's not interesting, so that one was 1 over 10,000. This one was 50 over 10,000, and then weight 2, 3, 4. So for each one of these, what I show is the edge labeling, and then this little corner here, upper right, shows the path. The labels that are used. For example, you see 101 here. So it starts from the middle. So start from the root, go this way, 101. After that, I have 010. You see here, they match with this 010, etc. So these are the labels for the edges. These ones are the labels for, these ones are the labels for the paths. This, for example, says that the path label 1 followed by 4 zeros is used 25 times, and I sorted by the number of occurrences or uses of these path labels. So we wanted to extract from these path labels the smallest number that would give us a binary subtree. So it would be comprehensive enough to include a binary subtree, and turned out for example, this particular one, it is say 7, the one that we are looking at now. So there would be a link, and you would be able to see it better. So these are the confidence intervals for weight 5. Let me see whether I can use this to scroll down. So confidence intervals. Right, so these are the confidence intervals. By the way, you see three box plots. The one down in this corner here, the one down in this corner is for the completely random generation of those. The upper ones are when you use certain methods to make the trees of higher weights. So I had, in addition to purely random generation, I used 2 structured random ways, let us put it. So we don't have time to talk about those, what's the structure of those random things, but these are on one hand random, on the other hand structured, but purely randomly. The mean is around 4, is below 4 actually, 3.8, 3.9, something like that. But with 2 methods, 2 different methods, you can make it higher, closer to 6 for the weight. And then this is the issue of z numbers, and when I multiply a number by powers of 2/3, whether or not the fractional part remains to be less than 1/2. What if we go backwards? So I was looking for numbers so that the stopping time before that bad thing happens, namely that the remainder of your number when multiplied by 3 becomes 1, and so the process would not be recoverable backwards. So I wanted a large stopping time. So this is like combining two rarity issues in base 2 and base 3. And the general belief is that these two bases are independent. So these two bases are independent. And if something is rare with respect to these two issues, it makes it even more interesting. So that's what I did here. So this is about to finish the PDF file. So this is the purely random generation, the approximate percentages of weight 1. I got nothing. Completely randomly, I got nothing, but I showed you how to construct. I constructed and showed you some of the weight 1/3 of depth 5, and then about 1% the weight 2, and so on, right? And then the other two rows are when I have some special structured random generation. So here is the some links to these things. For example, if I click on here, it will send me to those weight 1. 3 is weight 2, weight 3, weight 4. The weight 4 is the least exciting because we just said it's 55% of the time. So these are least exciting. So it sends us to this collection when, so 250 of these I posted, right? So this is one of those of weight 4. So this particular labeling. Now, what I did here in order to illustrate it better was, so in this box, blue means 0 and red R means 1. So I translated the 0, 1 to blue and red. And then this number that you get in base 2, I rewrote it in base 10. That's what you see here. So I call them the serial numbers. I was thinking of these as, say, bills. Like money, right? So serial number. And this particular serial number gives you weight 4 here, as you see here. Weight 4. And the individual children of these three, these three here, this ternary tree of depth 4, the first children has weight 4. The second children down here has also weight 4. The third child here has weight 3, and then pairwise they have 4, 4, 4, and it makes the weight of the whole ternary tree of depth 5 equal to 4 as well. So that's weight 4, and then I show here, a particular binary subtree that uses only 4 path labels. So this path label, blue, red, blue is used 10 times, and there are 3 more that are used these many times. Of course, there's some would be 32 because there are 32 path labels that you need for a binary subtree. So this is a weight 4, and it would be similar for the. I'm not sure when I was sharing that whether the screen was changed or not. So anyway, now. These were the weight 1 through 8. And then let's look at this one, for example, so weight 8, of course, and weight 7 are more exciting, right? And so weight 1, 2, 3, 4, I generated 250 of those. I said it's enough because either easy to construct or not interesting because there are so many of them. Weight 5, 6, 7, and 8, I generated much more, many more there. I guess in weight 7, I generated 2,900. In weight 8, I generated 3,000. So if I click on that, it would send me to that collection of 3,000 weight 8 threes. Okay, so that's that. And then MR stands for Mahler-Ramsey. So the first property we talked about, I call it Ramsey. There was this mathematician Ramsey last century, and his work relates to this. So I call that Ramsey property when we want to talk about the weight of ternary trees. And the property about fractional parts being less than 2/3, that sort of thing, is Mahler, another mathematician. So this is a coincidence of two rarities, rare in terms of Mahler, also rare in terms of Ramsey. So if we let me maybe stop the share, make sure that I share the correct thing here. Okay, so it's this one. Right, so we are looking at these things, and so you see these are more involved. Okay, so let's click on one of these, and what we see here is more than what we saw before, because now I would have a so top here would be your the green number there is the serial number. That makes this interesting, and by the way, this serial number is 110 digits. I wrote it in base 3, so 2s and 0s and 1s, that's base 3. Base 3 has length 229. And then the Mahler property and those 3 functions that I defined. So you see the stopping time for this is 234. And then the ultimate that you could have hoped for, which is not realizable, is 620. So about 234 of the times, when you do those those 3 functions, you keep going for 234 times. Remember, we had functions A, B, C, D. So one of them is 234, 233, 235, big numbers. So it means that the fractional part stayed below 1/2 for so long. This one means that the remainder was either 0 down here, the bottom here, was either 0 or 2, never 1 until you reach the 233rd iteration. And over here, the 2 situations, when you each time you multiply by 2/3, so consider 2 processes. One process is each time multiply by 2/3, and only at the end take the floor, round it down. The other process would be each time multiply by 2/3, and right then take the floor, round it down, and then, only then, after you have rounded down, multiply by 2/3, and then round down. These 2 processes would stay the same for 235, for this particular serial number, 235 times, they stay the same. So rounding only at the end matches with rounding at all those intermediate steps. So you see, the difference of 0, and all of a sudden at 235 or so, 35th iteration, you see sometimes they are sometimes they are equal, the dark brown here, and some which is height 0, and sometimes they differ by 1. So this particular serial number was special in base 3 in these 3 senses, and it is also special in the sense of Ramsey, in the sense of base 2. Why? Because the weight is 6, as you see here, and here is a binary subtree extracted from that uses 6 binary. Uses 6 path labels. So these things here are exciting, rare. In terms of 2 aspects. All right, so now I guess I would go to stop the share and go to the other one that we started the hour by. So now, for the sake of people, so these are the things I just described. These are the things that I have posted over the last couple of years. What I have been looking at the last few months. Oh, sorry. Yeah, let me share the screen now. So I go back to the mathematical notebook file, and yeah, I wanted to consider another interesting function. So one of the most well-known and unsolved mathematical problems is the 3x plus 1 problem. Think of the following. If I give you a number, and if the number that you receive is even, you are going to divide it by 2. If the number is odd, you are going to multiply by 3 and add 1. And of course, if the number is odd, you do 3x plus 1. If x is odd, 3x plus 1 is going to be even, because 3x would be odd, 3x plus 1 would be even. So why not divide by 2 if we are sure? Well, we are sure that it's going to be even. So the shortcut version of the problem is, if you have a number, if it's even, you divide by 2.
If it's odd, do the process of 3x plus 1 over 2 to it. In other words, multiply your number by 3, add 1, divided by 2. It's one of the most difficult unsolved problems that could easily be described as follows. No matter what number you start with, you are going to end up with number 1. This has been open for since 1930s, and many mathematicians have worked on it, and they think they say that mathematics is not ready to answer those questions. So mathematics is very rich, but still is not ready to answer that. So what I did was I wanted to have big stopping time. If we are not sure, and by the way, about up to 10 to the power 21 or so, it has been verified numerically, experimentally, that the conjecture is true, that no matter what you start with, you are going to end up with 1. So because we are not sure about the whole thing, and by the way, there are examples in mathematics and in number theory when the first counterexample is so huge. Therefore, having it check up to say 10 to the power 21 or so is not a proof. So what I'm considering are numbers in the neighborhood of probably in 10 to the power 108, 10 to the power 109, 10 to the power 110. Why? Because those numbers, when I write in base 2, they would have enough base 2 digits to go around the circle, label those. So once again, now I'm interested in rarity in the sense of Ramsey, those 3s of depth 5, so that when you label the edges, the weight of the 3 would be among those unusual ones. What are the unusual ones? Anything that's not 3, 4, 5. If you could get 1, 7, 8, that would be huge improvement. What I got was 2 and 6. So 2 and 6, remember, they were rare there, about 100%. But now we are combining it with big stopping time here. And I did search for 20 million numbers in the up to 2 to the power of 363. Remember, because those 3s of depth 5, they have 363 edges. So I need 363 labels, which are either 0 and 1. So that's why I work with numbers of this size. When you write it in base 2, you will have enough of them. And by the way, if it's short by 1 or 2 digits in base 2, you are going to append a 0. So include a 0 or 2 at the beginning so that the length is exactly 363. And the 5 numbers, okay, thank you. So the numbers that I got have these many digits, 110 or 109 digits in base 10, and the log 2 would be about 362, 61, or 63, as you see here. So when I consider those 5 numbers, so by the way, my point here is that these 5 numbers are very special. These are very special. So this is like a 2 people who are here or watching this, because these are not yet posted. Okay, so I'm going to be working on numbers similar to these, and they are interesting because my 5 numbers, they were chosen on purpose. So one of them weighed 2, 3, 4, 5, 6. This is one aspect. This is the Ramsey aspect of it. And what is the other aspect? The other aspect is the stopping time for the 3x plus 1 problem is big. And by big, I mean more than, if the weight is 3 or 4 or 5, then the number of standard deviations above the mean, you see here, these 6 point something, 6 point something, 6 point something. These are how many standard deviations above the mean your number is. So 6 standard deviation above the mean is very, very unusual. And if, on the other hand, the weight of the 3 was 2 or 6 in the sense of Ramsey, then the number of standard deviations above the mean is over 5. So slightly less than 6, but at least in the other sense is stronger, because the weight in terms of Ramsey was 2 or 6. So I think I would stop here, and thank you for your attention. Are there any questions, people here?
All right, so yes, we have,
All right, I'm just going to join in to say thank you so much for doing this today. I appreciated it, and I feel like I've learned more math today. So this is really good.
Yeah,
At home, we will be putting this onto our YouTube channel, and that way, if you want to get a little more look at it, that would be great. And thank you for supporting the CTL. Thanks, everybody.
Thank you.
Thanks, Eric.